Properties. Oh, there we go. Oh, that's not good. Okay. All right. All right. I don't know why that works. So I'm going to actually restart. That sucks. Thank you, John. That's embarrassing. That's a
Mission failed. We'll get him next time.
It's a mission failed. We'll get him next time. Why is this? Oh my gosh. All right, there we go. Okay, so mission failed. It's unfortunate. It really is unfortunate, but I'm gonna restart because that's bad. I'm probably gonna make this private and then edit it later and re-upload, or I think I could do that through YouTube. But I'm gonna restart. Sorry about that, guys. Didn't mean to waste your time. So now that you guys can actually hear me. So I was really busy this weekend with doing a hackathon. So I was unable to make my own code sort of resource this time around, but I was able to find a resource on Kaggle, and I think now is about time for you guys all to make your Kaggle account. You can use your Google account, but basically I made like a custom Kaggle one for us to use, and it runs all the way through. I've tested it a couple of times. And so basically just go to the link in the description that I have here in the live stream. You can just click this, go here, and then press, I think there should be like a copy and edit thing here, a button for you guys, and basically that's it. You can go in there and see the notebook and everything run as you please. The model actually did take like an hour and a half to make, just because it was just a lot of data that I had to process. However, I did train the model called model.h5, and we will show you guys how to load those models later. And that's pretty important because we are going to be using pre-trained models pretty much for the rest of this, for the rest of I guess sort of ML Monday, because I'm going to give you guys some models. I'm going to ask you guys to refine them, which is adding categories, adding stuff to the neural network, which is one of the very powerful things about a neural network, is it's able to take categories that it's never seen before and train new categories, unlike a lot of other types of machine learning, like support vector machines and random forests, which we did talk about earlier. So today we're going to start with talking about the model and how it was constructed, and then we're going to go and talk about a pre-trained model that you guys can use that does image classification for over 512 different objects, and we're going to talk about how the convolutions work in that model, and show you guys what it looks like after the convolutions in that model. So to start out today, we are going to go here, and we're basically going to, if you want to go, I put how to run from Kaggle, so you basically just go to the link and click the link. To run locally, you have to go and download the data and copy and unzip the files. I put it in the resources lectures data, which is right here. You guys can do whatever, but basically, if you have that and you've downloaded the data, or you're on Kaggle, I tested Kaggle again. It worked. So if it's not working for you, let me know in the comments. And if you guys have any questions, please let me know in the chat. I am looking at it. It's just I get very focused on what I'm doing. However, I will look at it every once in a while when I'm like at a break. So let's start out. So first, these are kind of all the imports that we're going to start out using, and essentially you're going to run this zip file. So this begins by listing the directory data, and you should see test1.zip and train.zip. This is just like a test to see if you actually download the data and it's in the right spot. If you guys want, you can put it sort of anywhere if you're doing it locally. But to unzip the file, you basically take the path to the zip file and then you add the directory you want to extract to, and then you just run it here. So in my case, I put it in data in the zip file and I extract it to these directories. Since I boofed up and didn't put on my audio for the first 10 or 15 minutes, yeah, it's a
Mission failed. We'll get them next time.
It's a mission failed. I am not going to talk more about this, how to set it up. If you guys have any questions, let me know. I'm in Discord, and if you guys want, type it in comments. Now that we're here, we're going to kind of define some constants. So for fast run, if you only want to like run it and make sure it works and only get about 70 to 80% accuracy, you can add this. And basically what we're doing is we're defining an image width. We want a 128 by 128 picture, and then we're defining the image size, and we're adding the number of image channels, which is red, green, and blue. So here we basically just create this prepare training data where we list all of the files inside of train, which would give you a file of basically a list containing all these file name strings. And what this basically does is it since this is a list, it goes through each file name in the list and it splits the file name into an array based off of the dots. So the 0 array would be cat, the 1 in the array would be 0, and then the 2 in the array would be JPG, and on this one a cat would be 0, 1 would be 1, and JPEG would be 2, etc. So this category, what we basically say is if the category is dog, so there's only like cat.0.jpg and dog.0.jpg. What I did last time was I just split these into their own folders just to show you guys how to do categorization from separate folders, but this time I used the actual data set that was in here just to show you guys different ways that the data can be organized. So now that we're here, we have this data frame, and this is kind of what the data frame looks like. It's just a file name, a category. So basically it's just a list of file names and then what each sort of file name or the sort of image in the file name contains. So after this, we can kind of see the value counts of each one, 0 being cat and 1 being dog. You can see that we have a sort of exactly even distribution of cats and dogs, which is 12,500 cats and 12,500 dogs. This guy actually got it wrong, but here's how to load like sort of any image in Python. You basically just what this does is basically just gets a random number, a random sort of part of this array, and then it chooses that file name, and then you can load the image in from that file name. You can plot, and then the plt.im show just shows the image that you loaded. Now that we're here, so this is how we build the model. So this is how the model that I created was built. We have we start out with 3 convolutions, and then in each convolution we have a normalization, a pooling, and a dropout, which I will talk about later. Those are really cool functions that we can use to actually see what sort of extract the features from the 2D images. If you guys don't remember from last time, or if you didn't watch last time, convolutions are basically just a like if you have a image, it goes through each image and it like it basically sort of adds all these numbers up, and it's called this array that it uses to create the function is called it's called a batch, I believe. I actually don't remember. Again, I didn't have it a lot of time this time around, but we will get to this. We will get to this later. I'll actually look at it right now. Kernel. So this right here, this 3x3 kernel, it is kind of showing us what is kind of happening with this 3x3 kernel. And if I pull up the slides from last time, so I'm going to kind of walk through this in a little bit more detail. So if we have like a convolution that's 3x3 and we randomly generate like a bunch of these different convolutions, we can basically create a bunch of different images that all create different features, or that all extract different features, right? So if we have this function that sort of extracts a bunch of different features, we can go through each function, and then if we have this matrix here, so if we have 3 plus 1 plus 2, that would be 6, and if we have -1 plus -7 plus -5, which would be -13, 6 minus 13 is -7, right? So that's how we create this output right here, yeah, so we have 3, 1, 2, and then 1, 7, and 5. We can kind of create a new image from this previous image based off of this matrix. And what the convolution and what this neural network is doing here is it's randomly generating a 3x3 matrix that basically it's randomly generating a 3x3 matrix that goes through and creates a new feature map every time. So this is creating 32 different feature maps. And then what this batch normalization does, and I put the documentation here so you guys can see it. You can see we've set the filters and the kernel size, and you can do strides. Strides are basically how far it moves after each sort of calculation. I don't really use the rest of these ever. Padding is never really used. It's never really changed. This is kind of just default stuff that if you're getting sort of really deep into the neural network stuff, you can add that. So at this point we have batch normalization, which basically just takes the output of what we got from the convolution, which is just a bunch of images, and it takes those images and it scales those between 0 and 1, so it's easier to work with in our model. And what this does, this max pooling 2D, is it basically it takes the 3x3, it takes the convolutions that we made, and it resizes it down, so it's easier to work with as well. So what this max pooling does is it takes the convolutions that we got from before, and it basically creates a new smaller image, and then after that this dropout layer drops out 1/4 of these, randomly drops out 1/4 of these convolutions every time it goes through. So one node of our convolution is not more highly weighted than the last one. Okay, and so by this time we have this dropout and we have this convolution. So this generates 32 feature maps, and then afterwards we have it generating 64 feature maps, and then it has 128 feature maps, and then it sends all those into the neural network. So basically the same thing. It creates 64 unique feature maps from the input based off of a 3x3 kernel size, and the activation function is ReLU. So let me talk about activation functions. So activation functions are basically functions that help you define what's changing, essentially. So if you have, I talked about it last time, activation functions are, let's go up. There's a bunch of different types of activation functions. The one we're using today is the rectified linear unit. And basically what this does is it sets a max between 0 and whatever is, and like whatever the actual value is. So like anything that's negative doesn't actually get counted towards the end product. So it doesn't go like below 0, and it's just a regular and then after 0, it just becomes a regular linear regression function. Right, so same thing here. We go to this batch normalization, and it basically normalizes the same thing. It goes between 0. It takes the output of the function and goes between 0 and 1. And then this pooling resizes it, and then we do that again, but instead of doing 64 feature maps, we do 128 feature maps, and then we send all these feature maps that we get, all these feature maps that we get, and we send it into this flatten function. This flatten function basically takes a 2D array and flattens it into something, and basically flattens it so like the first row of numbers in the image goes right after the second row and then right after the third row. So basically just takes the array and puts it into a 1D array, which is super useful and helps us. It is just a useful function. So after that, we call this dense function, and this dense function is basically where the neural network comes in. It has a bunch of weights and biases. So the initial weights are not actually set, but these biases are what our model uses to like actually train and learn. We'll talk about a learning rate later. Learning rates are very important for how the actual model works. And we can actually change the learning rate while we are training the model. So if we start to get really accurate and we don't really want to change the model a lot, we can change our learning rate, and that will help us sort of really hone down what we want to see. And now we have the model add, and then after we do this dense layer, we just normalize the sort of output from that. That outputs 512 that outputs 512 so that would be this layer here. That would be the layer right before, and what that does is it just creates 512 different outputs for us to then create 512 separate nodes or like biases for us to train and change as we're going, and so we can then sort of add all these weights and create an output. So we want to drop out half of these every time. I don't know why he chose a half on this model, but he did, and it actually turned out really good. He got 90% accuracy, and it worked really well. And so basically, once we've created this model, we are able to compile it and get the summary. So when we compile it, we establish a loss, and the loss is very important for how the model works, because the loss determines how sort of accurate the model was. So categorical cross-entropy basically means if you have like two categories, and one of the categories, if you get one category right and it's closer to another category, it basically keeps track of how all the categories are related, and if you like get it like a category really wrong, it weights it higher than if you were to get like a cat versus a tiger, or like a wolf versus a dog would be weighed a lot less than if you so if you were to guess like a cat and it was a dog, it would be weighted a lot more than if you were to guess a wolf when it was a cat, etc. It basically just weights the loss in a sort of easier fashion. And once we do this, we can compile a summary, and we're able to get this summary. As you can see, the input shape is 126 by 126, and this is by 32. So this creates a 126 by 126 sort of image, and it has 32 of those sort of images, and that makes the parameters 829. Batch normalization takes the same exact thing, and it basically just it just puts it into a number. It takes all the numbers from the convolution and just puts it into it just weights it between 0 and 1. This max pooling basically takes our image and makes it smaller, and we're able to actually have a 63 by 63 image, and it's just a way of making the image smaller and easier to deal with, so we can put it into our neural network more effectively. And then we do this a bunch of times. We weight these sort of, we create another convolutional layer with the same sort of so this one was also a 3x3 kernel, and this kernel was 64. So now 61 times 61 times 64 creates 18,496 parameters. Well, no, parameters comes from parameters comes from this here, because it's 63 times 63 times 32 parameters, because this is the all the data that it needs to generate this output. And then we just keep going. We have a couple layers of convolutions, and then we flatten out this. So if I pull out a calculator, and we have 14 times 14 times 128, you can see that our parameters create 25,088 sort of, so like that would be our input layer into our neural network. So at this point, we haven't even started the neural network yet. We've just created our input layer. In this model, we only have one hidden layer, which actually the one hidden layer gives us like 90% accuracy at the end, which is really good for determining whether something's a cat or dog. And if you look at the README, you can see that the cat or dog sort of helps you determine the actual. You can see some sort of example images and whether or not it guessed a cat or a dog. Now, after this dense, we do the same thing. We do a batch normalization, and then we take out some of these. We take out some of these, like 50% of these sort of layers. So we take out half of these. So like we don't have some biases a lot higher than other biases. It kind of helps keep the biases sort of it helps keep the biases less biasy, so it doesn't rely on one. So for example, like if this one was like 300 and this one was like 0.5, if this layer it would be very reliant on this node to determine the output, and we don't want that, because that's not very helpful for us. And then at the end we do another dense, but instead of outputting 512, it only outputs 2, and that is because we have a dog or a cat. So in total we have 12,942 parameters, and we only have 1,472 trainable parameters, which come from these convolutions, these 3x3 convolutions, and these whatchamacallit, and the where is it, dense layer. Okay, so now that we talked about how this network is sort of built and how it kind of works, if you guys have any questions, let me know. Now that we've kind of talked about how these layers kind of work and how they sort of interact with each other, what they do, there's these things in TensorFlow called callbacks, and we have a bunch of these different callbacks. Basically, I only use early stopping and reduce the learning rate on plateau. What early stopping does is, while you're training, it checks every time to make sure that your loss is going down while you're training. And if it if it just stays the same, or your loss is going up after a bunch of trials, then what it does is it stops your epoch early and goes to the next one. The reason that's good is because your biases don't change. So let's go back to the thing. Your biases don't change between epochs. So your biases change between epochs, which means like for the entire epoch, your bias is the change, and all we're doing is changing the weights, right? And then afterwards, we change the bias to fit the validation. And so basically, we just set this parameter to patience is equal to 10, which is basically just saying that whenever the validation loss is the same or greater than 10 times in a row, it stops early. That's all that means. And this reduced learning rate on plateau, we have we can like monitor. We can change what we want to monitor. So if we have some other metric that we want to sort of reduce the learning rate on, we can change it to that. However, I did a validation accuracy. The patience works the same. It's the number of plateaus in a row before changing. So if you get if you can change this to 3, and if say the validation accuracy is the same twice in a row, it reduces the learning rate, so it becomes so it learns slower. And verbose just means we print basically every time we change the learning rate. We didn't print here just because it doesn't really affect it doesn't really affect it that much, because again, we're doing this because what it's doing doesn't affect it that much. And then we set a minimum learning rate. You don't have to do this, but I did it just because pretty much anything less than this is useless, to be honest. But now we just take these callbacks that we created and we put them into an array, and we're able to add these callbacks when we compile when we go to run the model. And later on, we'll learn about this program called Weights and Biases that keeps track, live track of what of how our models are performing, which is really cool. So here, all we're doing is we are preparing the data. We're changing the categories that we created earlier in this data frame. So the data frame, remember, from way up here, looked like one column was file name and the other column was category. We basically just changed that. So it's instead of 0, it's cat, and 1, it's dog. And then we call train test split again, which we went over in week 2. We're doing a test with smaller test size this time around, because we don't actually have a lot of data to deal with, which we're going to talk about how to deal with that in images later on, how to deal with having a smaller data set with large data sets of images. And we basically just reset because so if we were to not do this, all these sort of indexes would be all shuffled around, and it wouldn't be from 0 to 1 continuously. It would kind of jump around from 1, 2, and then skip 3. 3 would be in the validate, and then 4, 5, 6, 7, and then 9 would be in the validate, etc. What this does is basically just resets the index, so it's easier to deal with. So these are basically the counts of all the of what we did. We have about 10,000 dog and cat in our train, and about 2,500 dogs and cats in our validation. So we set our batch size as 15. So our batch size is important because it's basically what sort of image data is loaded into memory and is trained. It is trained sort of every time while we're training. the batch size can change, but 15 was what the guy that made this used, and it turned out really good. I didn't really have time to go and change all the variables this weekend because I was in a hackathon. But I encourage you guys to play with some of these numbers and see if you guys can get any better results than me. So by this time, we will have a image data generator. So an image data generator is a way to change the sort of images that are flowing from a directory, and so we can like rotate the image, we can rescale, so we can rescale the image. So this is basically normalizing all the numbers inside of the image and dividing by 255 between 0. So it puts it between 0 and 1. That's because all the data inside of an image is. So each pixel is a number between 0 and 255. This basically just makes it so each pixel in the image is between 0 and 1. The shear range basically just makes it so you can shift the image left or shift the image right. And the zoom range just makes it so you can zoom the sort of image in and out. And the horizontal flip means that the image can be flipped one way or the other. And the wide shift range basically just means it basically is able to. Oh wait. Shear is shear means that it resizes the image and just adds like random data to the left of it. Well, not random data. It just sort of extends the images. Shift moves the image, and it fills out what the image is supposed to be, and it fills out. So it's a lot easier for you to see what's happening with an example. So we can kind of see this image. So these all kind of look the same to a human, but to a computer, these all are completely different images. Like you can see like this shearing happening here. And it's rotated, so like you can see the image rotated and it's sheared, and you can see it generates like just takes the pixels on the side and sort of extends it out to the right or the left or up or etc. So we can create a bunch of random sort of images from the same image, and so our model doesn't have sort of biases between whether or not it's like rotated or not. It doesn't really matter now whether or not the image is rotated or zoomed in or to the left or the right. It is able to categorize like pretty much any image. So that's what this does, this train data gen. And once we have that, we can kind of go into, so take our train df, which we from our train test split, with our file names and labels, we're able to then define the directory that all these image names are from, and then the X column, which is just the file paths, and then the image labels, and then we are able to set the size of these images, which we set before, and then class mode. So this changes the output type. There's 3 different types: categorical, binary, and sparse. We chose categorical because that's what we're doing. Binary basically just means 0 or 1, like yes or no. And then sparse means you can have like a bunch of different. Sparse means you can have like a bunch of different categories, and then each category is 0 or 1. Categorical basically finds the probabilities for each category and then takes the max at the end. So we do this. So after our example, so I kind of showed you guys this. So we basically just take one example from our data gen and we show it in this randomizer, and we show that, so we only have one image in our data set, but it creates a different image every time. So our model can sort of adapt to rotations, movement. The dog doesn't have to be in the same portion of the picture every time. So we're basically just generating a bunch of new images from the same image. And after we fit this model, so this took a minute. So as you can see, every model, every epoch took about 80 to 90 seconds. And I have a beefy computer. So this, it took a while. It took about an hour, hour and a half to run. And I ran 50 epochs of this. And by the end, the validation accuracy was 92%. The training accuracy was 90%, and our loss was very good. As you can see, our validation loss is actually less than our training loss, which is a really good sign that we could keep going. So after I was done training this model, I saved it so you guys can see it. I uploaded this to the GitHub. So the reason this neural networks are really cool is that you can keep training a model on new data and just keep training it. And what that means is basically like if you guys wanted to use the model that I made, you can basically go here. Where is it? You can go here and just load the model and then run these prediction stuff, all this prediction stuff that I'm about to do here. Model.save weights. So after that, we can do visualize the training. So we have this history variable from when our model was being trained up here. So when we fit the model, we said history is equal to model.fit, and now we're able to take this history model and graph it in matplotlib to see how our model did over all the epochs. And as you can see, it looks really good. There's one sort of outlier, but that'll happen where the validation loss was a lot different than the training loss. But that's just how the cookie crumbles. So we kind of want to do it so it keeps going down like slower and slower. So we don't want to overtrain it, but being able to look at a graph like this and knowing like, you know, it's hit a plateau, like it's not going to get any better is kind of when you're supposed to stop or find more data. Again, you can always find more data to make it more accurate, right? Your models are only as good as the data that they're trained on. Oh, that was a good quote. Your models are only as good as the data they're trained on. So the more data you have, the better your models are going to be. Prepare testing data. So here we're just showing a bunch of testing data. So to predict something, you basically just take this test generator, so wherever your test stuff is, and then you take like you can put like an array of images in there. You can pretty much put anything that is of target size, 128 by 128 with three colors, and basically throw this in here, and it's able to generate a sort of prediction for all those images inside of that generator. And by this time, you basically just go through. This is just some stuff saying like model.predict. This is just creating the test data frame. This is just taking the test data frame that has all the file names and putting a category next to it, right next to it, and then here is the dictionary. So we have a label map. We have class indices. We have the test category, and then we replace this category with the label map, which is right here. Oh, it's right there. and we replace it with a label map, which basically just takes all this train generators stuff, all the things that are inside of all the stuff that we generated from before, and it replaces the. So if it was like a 0 or a 1, it like it basically creates this dictionary, but it's an automatic way to create the dictionary, so you can add more categories later. So, oh wait, what? I honestly don't know what this does. Hold on. Class indices.items. Class indices. Oh, okay. 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 This is just indices.items. I don't know what this does. Decay v. Sorry, guys. That's an oof. Say. No. I don't know. I will let you guys know if I have if I know what this means later, but I don't want to run it right now because that will reset my outputs, and I don't want to have to run this for another hour and a half. Yeah. So basically, because my computer crashed, and it reset all my variables, which sucks. So if you have, so now that we're down here, so here's a better way of representing the image that I have in the GitHub. As you can see, this guessed, so 1 is dog and 0 is cat. It guessed this picture correctly, it guessed this cat correctly. So this cat was incorrect, but it's not really facing the camera, so you can't really blame the model for that one. You see the rest of these, I kind of went through dog, cat, dog, cat. As you can see, it's doing really good for most of these images. It only really got one here wrong here, but that's kind of why I chose this image. I ran it a couple of times and waited for it to get a wrong image, but that's because most of the wrong images are most, if you have like 90, in the like range of 90 to 100% accuracy, most of the stuff that you get wrong is pretty reasonable. And so now that we're here, if you guys want to use the model that took me an hour and a half to generate, you can go onto the GitHub. If you were to pull it, it should actually come back. This model.h is actually not very big, so I'm going to pull this up in a file explorer. Pull up week 4 properties. As you can see, it's only about 50 megabytes. So this model that I output, it's only about 50 megabytes, represents like a gigabyte worth of sort of image data, but you could keep training this model. So the really good thing about this is that you could keep training this model and keep training it, and it'll always pretty much stay 50 megabytes. So you could train it on thousands of gigabytes of different sort of images, but it will always be around 50 megabytes. So that's where we come to a bunch of different this pre-trained model by Cornell called VGG16. VGG16 is a sort of image classifier that classified 512 different sort of species of like flowers, pets, sort of animals, different things, different images, and you can see the summary of VGG16. It has a bunch of convolutions. It does max poolings, convolutions, max poolings, all this stuff. But essentially, what it does in the end is it takes. Let me see if there's a way. So it basically just does these convolutions. It creates 64 convolutions, and then from those 64 convolutions, it creates another 64 convolutions. This is basically just a feature extraction method that Cornell created to help with sort of image classification. So now that we're here, you can see it takes about the same amount of parameters as ours. So by the time we get here, I'll actually run this. Hold on. Is it gonna run? That's the real question. PLT is not defined. So we can run this here. We can take like a bunch of these sort of cat images, and we basically just, all we got to do is just import VGG16 from Keras, and now we have a classification model, and we're able to see. So if you take this image here that I did, so I basically wrote this sort of thing that just gets a random sort of integer between 0 and 1,000 from our test set, and if we run this again, it'll just get a new random image. And you can see from the random image that we created, pre-process input. So 224 by 224. Yeah, I had that. So you can see these were the features that were extracted from the VGG16 convolutional feature extraction. So here's basically, all you have to do is just create the image into an array. All this does is it just takes the image type and converts it into an array model. And then we have to reshape it into a 1 by, so this is expecting a bunch of images, but we only gave it 1. So if we do another image, we can see that it did a feature extraction like this. So your eyes kind of, when you look at an image, your eyes automatically do all the feature extractions. Like your eyes automatically do this, and all the data processing is done automatically. But in a computer, it doesn't know to do that image processing. In fact, a computer, when you first get it, doesn't even know what an image is. So you have to give it. So you have to tell it to look at certain parts of the image. So this is basically what a convolution would look like. So all these layers turn out to generate from an image like this to something like this, which is kind of whack. So if you remember from last time, VGG16 is not deep learning. VGG16 is just feature extraction. What we did for today with the dog and cat sort of images, we did deep learning. The VGG16 has the feature extraction, and then it goes into classification, right? So the people at Cornell did all the convolutions based off of what they wanted to classify, and they did a bunch of trial and error and everything. So now that we're here, we can get these predictions, but let me see, is it going to output something? Yeah, you can see that it has a bunch of different outputs, right? Bunch of different outputs. But what we can do is then say, so let's just do the length of this output, right? So there's 1,000 different things that can be categorized. I thought it was 512, but there's 1,000 different things that can be categorized by this model, right? So how do we know what it classified it as? Well, we don't, unless we are able to decode the predictions, right? And so, this is supposed to be here, doesn't really matter. Basically what we can do is then put this into the pre-made decode predictions a function for VGG16, and we're able to see that this output an Egyptian cat, which is pretty good. I think that's pretty good. That turned out about right. And if we do this a couple of times, it will show another Egyptian cat, which I guess may or may not be right. So this gave us a, see how far away the actual subject of the image is, but it's still able to understand that is a Shetland sheepdog, which it may or may not be, but we are going to look into what a Shetland sheepdog is. It looks like this. I guess it has about the same face, right? Yeah, I could see why it could think it was a Shetland sheepdog. We go. Oh, my bad. We go to this dog here, and you can see how the sort of feature extractions are able to find like the right features that it needs for the computer to understand what's happening. And you can see that it output a whippet. I don't know. It's kind of funny. Whippet dog. It thought it was a dog like this. So basically what this model has spent hours and hours training on thousands, if not millions, of different images, and we're able to use what this sort of model has created and use that as a way for us to either hone down what we want our models what we want our models to do, or add new things for classification on top of this model, which we will talk about either next. I don't think so next week we're probably going to talk about how to do stock market quantitative analysis using neural networks, because I think that's a cool topic. And I hope you guys like this week. I was very busy this week at the hackathon, so I wasn't able to really code my own. I wasn't able to like put as much time into it this week as I was last week. But next week should be a different story. Next week I should have enough time to at least create a presentation or something around this week. But I was very busy this week. I hope you guys still liked it. I hope you guys go when you play around with some of these numbers and train your own models and do all that. But if you guys have any questions, I'll stay here for another 15 minutes since I screwed up the beginning. And I might see if I can get this to work. Other than that, I think I'm done for today. It is 7:30. I should be done, but again, I ruined the first part of the lecture, and what these things are. Oh, we could talk about losses for a little bit. So these are the different types of losses that you can have. And there's different categories of losses that you can have as well. So probabilistic losses are like if you were to have a bunch of different categories, or you want to classify stuff, there's certain probabilities. It generates probabilities instead of it generating like a 0 and a 1, right? So a binary cross entropy would just be one output, right? It would tell you, one number between 0 and 1. A categorical cross entropy would be a number between 0 and 1 for every single category. A sparse categorical, I actually don't know what this one is. Sparse categorical cross entropy. One hot representation. Oh, sparse categorical cross entropy is if you have a bunch of different categories, and it basically takes like the top ones that you had for that you tried to produce, and it weights what your actual prediction was. This one here, categorical cross entropy, doesn't weight what the actual percentage was. It just takes the max one. This one weights what you actually thought the percentage was. Binary cross entropy, boson. And so when you look at these right here, when we put them into a model, like when we were to compile our model, the loss right here, we could only use the function in there. If we wanted to set our own class, we could actually put in a whole class in there, like if we wanted to put in like a class, like let me see, it's like instead of this we could put like categorical cross-entropy in here, like that, and then define all the different stuff that we want for categorical cross-entropy. This just uses the default, and it's just a function. So yeah, that's kind of the difference. So there's these different categories for losses. These regression losses are if you're like trying to get a number. So if you're doing like image classification where you want to find something in an image, you would have a regression loss where it tries to sort of predict. So if you were to say create an image classification for finding something in an image like a ball or something, you would have a bunch of data having a picture of a ball, and then you would have like the left corner of the box where the ball is, and then the width and the height of the box. So then you would then take in the input of the image, and then you would generate out where the left corner of the box is, the x and the y of the left corner of the box, and the width and the height of the box as well. And you would use those all as a regression loss. There's a bunch of different loss functions. Mean squared error is the one I normally use, but there's a bunch of different ones that if you want it like really accurate, like it's very important that you are correct, having like a mean squared logarithmic error, or something that has like a logarithmic, which means like it's like super, like if you get like a really high number, like here, let me go on Desmos. So if you like log x like 2 to the x, right? You can see that if you were to guess like 4 instead of like 2 here, right, it would be a lot worse. It wouldn't be the same as if you were to guess like 50 and 100 if you were to guess like 2 or 5, right? 2 and 5 are a lot further away than 50 and 60, which this kind of helps weight how the sort of loss is calculated. Where did it go? Did I go here? Oh shoot. Where was I? Oh shoot. Oh well. Yeah, so it basically just helps figure out how the loss is calculated and gives you a sort of output. There's a bunch of different optimizers as well. So let me go optimizers. So so there's a bunch of different optimizers that you can use as well. The optimizers I use for this one was RMS prop, but you can use all these. The only other one that I'm familiar with is Atom, which is just how it changes the sort of bias after each cycle, and then after RMS prop, it's just how it, like the gist of RMS prop. So maintain a moving discounted average square of the gradients, divide the gradient by the root of its average. So the gradient would be like, I guess how the gradient is kind of, so I probably should have talked about gradients in my last lecture now that I think about it. But a gradient is basically how it helps add like a dimension to your predictions, right? If your predictions are better, your gradient is like more accurate, right? So if you have, it's a bias, but it's not really a bias. it's hard to explain. I'll research it more. I don't know much about them, I'll research it more, and I'll let you guys know next time what more about gradients, because I do need to learn more about that. But Adagrad, ooh, I've actually heard of this one. Adagrad is basically just a better version of Atom. Yeah, but there's all these optimizers you can use. You can basically just take like these names and just put them in here and try them all out. Again, I encourage you guys to go download the notebook and try out different optimizers, different metrics, different losses, and see, you know, what comes out the best. This is not by any means like the most optimized version of this model. You can always improve models, either by finding more data, changing the loss functions optimizers, changing the hidden layers. There's so much you can do with sort of optimizing a model. It's hard. It's kind of overwhelming. But if you just change one thing at a time and look at how it affects it, just use science, you know, have a theory of what you think is the problem or something you can improve upon, change one thing, and then if that one thing improves it, then you know that was a big factor. So yeah, that's it for today. I don't think there's anybody really watching live, which sucks. And yeah, I hope you all have a wonderful afternoon. If you guys made it this long, let's see. I hope you all have I can't do my exit sound now because I got striked last time. So yeah, if you guys have any questions, ask me in Discord. There was nobody here. There was only, I know, 2 of the people that were here live, and there's really only one other person, and I think I know who that might be. So I don't think there was anybody here live this time around. So if you people stop coming and there's no like, basically if nobody watches this, I'm just not gonna do it. I only do this because people watch it. And yeah. Finally, I'm done. that was just me. If you have any questions, let me know. And yeah, have a wonderful afternoon. Adios.